I can go ahead?
Yep, go ahead.
Okay. Good afternoon, good evening, good night, wherever you are in the world. Good morning, everything. What brings us to PASCOS? And more generally, what motivates our work? We seek surprises. We seek physics beyond the standard model. We seek to find changes to the standard cosmological history. And we seek to find new astrophysical sources. Neutrinos can be a powerful guide in helping us find such surprises. By avoiding the electromagnetic and strong interactions, neutrinos are exquisitely sensitive to new forces. By their high abundance, neutrinos are exquisitely sensitive to changes in the early universe. And by their penetrating power, neutrinos are exquisitely sensitive to new kinds of astrophysical sources and the interiors of such sources. And best of all is when we combine these techniques of neutrinos in the laboratory and cosmology and astrophysics. So I want to make a distinction. This talk is about neutrino astronomy. I want to be a little bit sharp in the distinction of what I mean between neutrinos in the laboratory, cosmology, and astronomy. So neutrinos in the laboratory is a precise, well-controlled thing. It's difficult to detect, but it's well-controlled. And we know that if we send a certain number of neutrinos from a beam, we can collect a certain number of neutrinos in a target. It's very predictable, and it's sort of like counting things one by one. In cosmology, we don't detect neutrinos one by one. We don't detect them at all. We just detect their bulk properties. So we just detect that there's a presence of neutrinos through their number density or through their mass density. And in neutrino astronomy, a bunch of neutrinos are thrown at us from a random direction at a random time. And it's our job to try to catch some of those and then to figure out something about the sources. So individual neutrinos are caught. Individual neutrinos give up their lives in the service of science. So why should we even try? It sounds hard. So neutrinos reveal wherever there's hot, dense matter, wherever there's hadronic acceleration, and wherever there's dark matter annihilation. All of those things basically ubiquitously produce neutrinos. And it's our job to find them. And it's very hard to conceal such sources because they make neutrinos and the neutrinos get out. So the cool thing about neutrinos in astronomy is they let us see inside the sources, and the flux is not attenuated, it's not deflected, the timescales are not slowed down. The only thing about it is that detection is hard. But in principle, neutrinos are an ideal astronomical measurement tool. It's just hard. But that is somewhat under our control. So if thinking about this, how is it even possible? There's some factors we can't control, and that is the question of whether nature provides abundant sources of high energy and high luminosity neutrino sources. And it does. We know that now, both from neutrino evidence and from corresponding evidence from cosmic rays and gamma rays. We know that the sources are out there. Factors that we can control is making detectors. So if the neutrino cross-section is small, we just need a bigger detector and lower backgrounds and all of that. And that's possible. It takes sort of kind of a crazy dedication. Those of us in neutrino physics have a lot of patience, and that it's worth it. And then there are parts that require wisdom. And that means that even though we detect neutrinos, initially the statistics will be very low. But by carefully leveraging that with other knowledge, then we can learn quite a bit, even from low statistics. So for example, if we see one Tyrannosaurus rex walking around on Earth, that tells us that dinosaurs still exist. We just need one. So the reason neutrino astronomy is so powerful is really twofold. First is to understand some of the most extreme astrophysical sources. We just can't do it without neutrinos, because only neutrinos can see deep into their cores to reveal the physical conditions there. That's multi-messenger astrophysics. On the other side, to fully understand neutrinos, we just can't do all of the experiments in the laboratory. In some cases, we need the extremes of astrophysics to reach the conditions we need. So that's our search for physics beyond the standard model. So I'll talk about three frontiers, three different energy ranges where we are hoping to make more and more detections. And then at the end, I'll talk about how do we turn this into a bigger subject. So on the MEV frontier, so far we've detected the sun and one supernova, supernova 1987A, but we know that there are all of these other things out there that produce neutrinos. Neutron star mergers definitely produce neutrinos. It's just so far we haven't found them. Flares from novae or supernovae may produce neutrinos, not the supernovae, but flares from them. Dark matter annihilation and decay is almost guaranteed. And there could be great surprises. That's why we look. So thinking about the sun, what are the motivations? The original motivation was to understand the astrophysics of the sun by seeing the deep interior of the star. And along the way came the second motivation, which is to figure out how neutrinos work. This theme, matching the astrophysics and the particle physics, comes up again and again. So what have we accomplished in solar neutrinos? Most of these fluxes have been detected, not all of them. The Hep flux has not been detected yet. The CNO flux has been sort of barely detected. These are great accomplishments, but it's not enough. We've also learned that neutrinos mix, and the combination of the SNO experiment at the top and the CAMLED experiment at the bottom were especially important for confirming that for every 3 electron neutrinos made in the center of the sun, 1 stays an electron neutrino and 2 become mu and tau neutrinos. And those have the mixing parameters that we now call the large mixing angle solution. That was confirmed in the laboratory with reactor antineutrinos. This is wonderful. And Nobel Prize winning work, but it's not enough. So what's left unsolved? The central mystery of the MSW effect in solar neutrinos is the energy dependent oscillation probability. And everybody talks about this like it's no big deal, but it is a big deal. And the low energy experiments have basically measured near constant oscillation probability at something around a little bit less than 2/3. And the high energy experiments have measured a near constant oscillation probability at something around 1/3, but nobody has ever seen the transition. The dynamics of MSW is the energy dependence. Nobody's ever seen that. So that needs to be seen. And for a long time, there has been a discrepancy between the reactor and solar measurements of delta M squared. And the discrepancy is a little bit less now, but it still remains extremely important to compare those two measurements. Sun is neutrinos with matter effects. Reactor is antineutrinos with vacuum mixing. So the very different physical conditions allow powerful tests. Why do we have hope to go forward? Well, there are lots of new ideas for low energy new solar experiments based on argon and xenon and other things. Those look very promising. Hyper-K is coming. There are new techniques to reduce backgrounds, and DUNE may be a very powerful solar neutrino detector. And I want you to contrast this figure from the one before. I'll just go back. The reactor region from CAMLED at the top is huge, and the solar region from the combined experiments is huge. And I want you to notice that once JUNO comes on, the reactor region will be infinitesimal. So whether or not these two delta M squareds agree or not right now, it doesn't matter. The important thing, one will have the error bars shrink greatly, and we want both of them to shrink the error bars so we can test new physics. DUNE looks very promising for that. So that's not all we can do. We can also look for multi-messenger astronomy. One of the puzzling things that's not well known about the sun, everybody's seen the pictures on the left, where the sun has been viewed in many wavelengths. On the right, I show the picture of the sun in, basically 10 to 100 GeV gamma rays. And maybe you don't know this, but the sun is actually blazing in these gamma rays. And the flux is something like 10 times higher than the predictions of the most optimistic model. So whatever theorists could do, the sun did 10 times more. So because we don't understand that model, maybe there's neutrinos too. So this needs further investigation. And coming back to the survival probability, as I mentioned, this is an exquisite opportunity to look for, beyond the standard model, physics that could change the energy dependence here. Turning to supernovae, the original motivation is, again, astrophysics, to see what's happening in the core of the newly formed protoneutron star. And then the tandem motivation is, again, to understand neutrinos. So we've seen one supernova, supernova 1987A. It's been a little bit too long. It's time for another one. And from this, we know that core collapses do emit an enormous number of neutrinos, and that they have energies of low tens of MeV. But there are many more supernovae to be found. And the total number of supernovae in the universe is several per second. So we want to find supernovae in three different distance ranges. We want to find them very nearby, like in the galaxy, where they're very rare but very spectacular. We want to try to find them in nearby galaxies where maybe we get like one event at a time in coordination with an optical burst. And we want to find the diffuse supernova neutrino background, which is the kind of steady glow of the universe in supernova neutrinos. And all of these things are in reach. And now that Super Kamiokande is adding gadolinium, the diffuse supernova neutrino background seems like very promising for the next discovery. Oops, sorry. So one of the reasons we have greater hope for what we're going to do in supernova and solar neutrinos is all of these new experiments. Super K is running, and the gadolinium upgrade is ongoing. JUNO is nearing completion. DUNE is on a great track. And together, these have great potential for neutrino astronomy, because Super K is very, very sensitive to nu bar. So is JUNO, but JUNO is also very sensitive to nu mu and nu tau, and DUNE is the best at being sensitive to nu e. So it's very important for a supernova that we have to have all of the flavors detected. Otherwise, we won't know the full picture. So on the multi-messenger astronomy side, we also want to find this thing optically. It's commonly thought that astronomers are looking at the whole sky all the time, and they really are not, at least not until experiments like the All-Sky Automated Survey for Supernovae, or ASSASSIN, which is now looking at the whole sky every night and has a great potential to find an optical transient early in the event of a Milky Way supernova. Still, we would like this experiment to be deeper, and so further experiments are needed. On the VSM side, supernovae, we expect a very strong matter effect. I've tried to draw the diagrams here for neutrinos interacting with electrons and having MSW effect. But the densities of neutrinos are so high that there's a matter potential from other neutrinos. And this has very important consequences for the supernova. And it's something we can basically never measure in the laboratory. It's basically a neutrino beam on a neutrino beam. So that's a really cool test of physics beyond the standard model that we can't do without astrophysics. So turning to the TeV-PeV frontier, main thing we've seen so far are the ice cube signals, but there's much more to be found. And the interesting thing about the ice cube signals is we don't really know what they are. We don't know what they are. And there's something making the diffuse background, and it's a mystery what it is. There are lots of plausible sources, but one by one, they all have problems explaining the data. We can also look for new physics. And as I mentioned, the cosmic ray collisions with the sun. And most of all, whenever we get a new telescope, we have the opportunity to find totally new things. So we hope for surprises. So the motivations here also go back many decades. People started dreaming about neutrino astronomy many decades before it made any sense. And those people were visionaries. And again, it's to understand the astrophysics and then also the neutrino properties. So what IceCube has accomplished is it's measured this diffuse flux of several tens of events above about 60 TeV, shown here in the data points. And the, I guess, yellow component is the astrophysical component. Definitely there's an astrophysical signal, and what causes it is not known because these come from everywhere in the sky. So unlike with gamma rays shown on the left, here I show the Fermi gamma ray sky, mostly the diffuse measurement of the Milky Way, and then of course many sources around the sky. In the same galactic coordinates, the IceCube data in this picture, which is old, I apologize, but IceCube has not made a new picture in galactic coordinates. The sky looks not so obvious. Originally, it looked like there was a signal at the galactic center, and that now has significance has faded. All the best data now suggests that the neutrinos that IceCube are seeing are isotropic from the whole sky, and you see less in the northern hemisphere because of attenuation in Earth. So there's a lot to be found out, and we need a bigger detector. That would be IceCube Gen 2, which is basically an order of magnitude bigger. And one of the other things we need is greater ability to separate flavors. Nu-E and nu-tau make showers, which look identical. Nu-mu makes tracks, which are separable. And we need new techniques to separate Nu-E and nu-tau. And in our paper here about echoes, we showed a way that that could be done. And this is important for how IceCube Gen 2 chooses its phototubes, because of the noise levels are needed to be very low to measure this technique. With the flavor physics, we have the best chance of looking for new physics, because then we can really have more observables. So IceCube obviously is a big contributor to multi-messenger astrophysics. There's one source, a blazar source that had a flare, that IceCube has a 3 sigma signal at high energies, and at somewhat lower energies, they have a semi-independent 3 sigma signal. And this is very promising, but you know, if it's real, we should start finding more of them and at higher significance. We're all very hopeful about that. And one of the other things that's leading the way is the stuff in gamma ray astronomy, which is really taking off. HAWK is measuring lots of high energy gamma ray sources. LASSO is just turning on. CTA is coming. By measuring the highest energy gamma ray sources, this will help us pinpoint which sources are most promising to be bright neutrino sources. Because something that's a bright source of neutrinos is also a bright source of gamma rays. It's not always the other way around. If it's just a bright source of gamma rays, that might be the whole thing. It might be an electron or electronic source where electrons are accelerated and doesn't produce neutrinos. But if it's a hadronic source, you produce gamma rays and neutrinos in basically equal numbers. This is very powerful for looking for beyond the standard model physics. IceCube and some independent theory authors have already looked for changes in the cross-section. The data is pretty crude, but it's pretty amazing that with this, you can already start to test standard model cross-section. Of course, IceCube data has also been used to set limits on neutrino decay, neutrino self-interactions, all kinds of things. Even though the number of counts is not very large in the IceCube data, we have a very powerful level arm because of the long distances, because of the high energies. Those make it very powerful. So on the last frontier, the EEV, ZEV frontier, that's 10 to the 18 to 10 to the 21 electron volts. So far, here's how many neutrinos we've detected. Absolutely 0. But we're very hopeful that they're there. And these might come from, well, they must come from the sources of the ultra high energy hadronic cosmic rays. If supermassive dark matter exists and it annihilates or decays, it must also produce neutrinos. And again, we could have complete surprises because nobody has ever really looked at these energies. With cosmic rays, we can't exactly look at these energies because there's a horizon for propagation of cosmic rays. For gamma rays, there's definitely a horizon, but for neutrinos, we could see much further and could find some really extreme sources. Again, the motivation kind of comes from astrophysics, the astrophysics of cosmic rays interacting with the microwave background. And it's also become testing the properties of neutrinos. So there are many experiments that have looked. I highlight one here, NEEDE. NEEDE is a balloon-borne radio antenna that flies above Antarctica. And if neutrinos interact in the ice, it makes a shower. The shower makes radio waves, and those radio waves can go up into the sky and be seen by NEEDE. And so far, they haven't detected anything, any neutrinos, but they've set important limits at high energies. And there's a successor experiment to NEEDE coming called PUEO, which will be much more powerful. So we're all very hopeful about that. And why? We're hopeful because we know that the ultra high energy hadronic cosmic rays are there. We don't know their composition. If it's protons, then we expect a very high neutrino flux. If they're nuclei, we expect a lower neutrino flux, but we just don't know. And there are some hints that they're protons and some hints that they're nuclei. And those hints come from the spectrum, the depth of interaction in the atmosphere, the dispersion of that, and possibly hot spots on the sky, which would favor a lighter composition. But this is all unknown, so we need new tools. And the hope we get for this is, Auger is being upgraded into having not only water tanks, but scintillator planes and radio detectors. And there are all these new neutrino experiments that are proposed to detect this ultra-high energy neutrino background. I want to highlight one that's particularly interesting. Most of these look for the sort of passively look for the radio signal from showers interacting in material. But the radar echo telescope is an idea where you do something different. You let the neutrinos interact where they interact, they make a shower, and you bounce radio waves off of those showers. And therefore you can detect, you're not dependent on the intrinsic brightness of the radio from the shower. You can make the backsplash radio be as bright as you want by using a brighter transmitter. So that has a lot of potential for very sensitive experiments. One of the other interesting mysteries at high energies is how all of these things tie together. You'll notice that on this E squared times phi plot, that the very roughly the flux level of gamma rays at the left and neutrinos in the middle and high energy cosmic rays on the ultra energy cosmic rays on the right, those all have similar energy levels on the plot. And because of the way this is plotted, the area under one of these curves is basically the luminosity density of the sources. So it's an important clue that the luminosity density of these three kinds of phenomena, luminosity density of the sources behind these three kinds of phenomena are comparable. So this has a potential for breakthrough connections between two or maybe three of these. These can also be used for powerful tests of neutrino physics beyond the standard model. I showed you this plot of the cross-section already, but I want to highlight that at the very highest energies, the GZK neutrino detection is probing, square root of S of like 100 TeV. So that's beyond the reach of the LHC, which is pretty exciting. And at those energies, there are large uncertainties in the standard model. So we could either find new physics or at least refine our knowledge of the standard model. Can't lose. We can also look for exotic physics like a Lorentz invariance violation. So to wrap up, how are we going to advance the goals? So I talked about looking for neutrinos on these three frontiers. But to really do this right, we're going to need a bigger boat than what we've talked about. So we talked about these three frontiers, but these have to not be done just individually, they have to be done together. Because what makes it astronomy? It becomes astronomy once we have many kinds of sources detected at many energies, ideally independent confirmations from different experiments, and most importantly, when we can tie those observations together, one neutrino observation to another and to electromagnetic and other observations through the power of theoretical physics. That's what's going to make it astronomy, when we have a plenitude of data and we can make sense of it with physics. But even that's not enough. Neutrino astronomy has to be broad, but that's not enough. We have to do something bigger, which I call neutrino science. And that is to bring together the laboratory studies with the cosmology studies and the neutrino astronomy. And the reason these have to be done together is, well, let's pick an example. Suppose there are sterile neutrinos, EV scale sterile neutrinos, maybe like those that have been claimed in the laboratory. Well, if that's true, it should change the number density of neutrinos in the universe and the mass density of neutrinos in the universe. And theorists wave that away by inventing new things. But those new things that they're inventing are at least as revolutionary as sterile neutrinos themselves. And so we need new ways to test this. And sterile neutrinos would alter the signals from neutrino astrophysical sources. So these are the kinds of things we have to put together to make sense of all of this and to connect it with the rest of physics, astronomy, and cosmology. So neutrinos are multi-frontier science, and they have a great potential to advance both particle physics, cosmology, and astronomy per se. So everybody has their own vision of the future. I think we're moving from a darker future to a brighter future. And I'm very excited about neutrinos being a big part of that. Thank you.
Thank you very much, John. We have time for questions. I don't see raised hands. But let me start with a question, John. Do you think we can learn anything about axion physics with by looking at neutrinos?
I'm not a specialist on axions. However, one of the next speakers, Peter Graham, is. And I think basically all of the arguments I just made about advancing neutrino science, I think Peter and others could wonderfully make about advancing axion science. And it's a lot of the same stuff. We need to combine the laboratory studies with the cosmology, with the astrophysics. And there's a really beautiful story to be told if it all comes together. I hope it does.
Right. And the question was really whether they are in a competition for energy. So you may, if you explain everything with neutrinos, you may not need axions in the other way.
Yeah. So for example, core collapse supernova could have novel energy loss channels to axions. On the other hand, we know that core collapse supernovae make neutrinos. And that's exactly why it's so important to measure all of the flavors. Supernova is supposed to make basically all six flavors, right? If we measure one flavor, Nui bar, we measure it beautifully with hypercameo-Conde with 10,000, 100,000 events, and we don't measure any of the other flavors, then when we try to get the total energy budget of the supernova, we just have to multiply by 6, which has a huge uncertainty. 6 is an integer, it's pretty well defined, but it's not necessarily well defined that all the flavors carry the same energy. And that's very, very crucial if we want to ask, is there room left for axions to be emitted? That's why I keep harping on we have to detect all of the flavors.
Excellent.
Yeah, actually, I just wanted to jump in there. Hi, it's Peter. Just to say, yeah, exactly. I completely agree with that and was going to say, indeed, measuring other flavors, we recently got interested in learning about axions coupled to muons, for example. The supernova could maybe tell you something about that, but right, we want to observe as much as possible, as much of the neutrinos as possible. So definitely we could learn more about axions even by observing neutrinos.
Great, great. Thank you, Peter. We have a question, and please go ahead. It's Zhang.
Okay, so the first question was about, in order to detect the EEV, ZEV neutrinos, what do we do? I'll have to skip back to that. I gave one example. Let's see. There we go. Here's an example is the NEEDE detector. So again, the neutrino interacts in the ice and it makes a shower. That shower makes radio waves. And NEEDE looks for those radio waves on a balloon. But lots of the experiments that I talked about on this page look for neutrinos, radio signals coming from the side of a mountain, from up from the ice, all kinds of things. But the radio is the key. And all of these are good ideas, very promising. Basically, they just need to be built, and they need to be built big. The only one that's really different from the other ones is the radar one, in which you try to send radio in and bounce that off the shower and have it come back. I can answer the other question here from Dr. Kirsten. Anita has not seen convincing neutrino signals yet. You're right. There were a couple of weird events that appeared to be upgoing a few years ago. It appears that those are not neutrinos. And there are some lots of exotic explanations of that, but there are also some rather standard model explanations. And there's a paper by Stephen Prohira and Krijn de Vries about not just a 20th century explanation, but I did like a 18th or 19th century E&M explanation of those events. So not only doesn't need new physics, it maybe needs some just super old physics. I think there's one more question in the chat. I see. We've learned a lot from Dr. Park. We've learned a lot from the CMBR. Is there any chance to measure the cosmic neutrino background in the near future? So, so neutrino astronomy is not hard enough. Already you want to make it harder by trying to detect the neutrino background. That's super hard, but it would be super important. In a sense, it will be detected soon once experiments like the large-scale structure surveys, like, some combination of, DES, DESI, the Vera Rubin surveys, Euclid, everything, all of those things, once they detect the neutrino mass density of the universe, that's really a detection of the neutrino background directly. Right now, we've detected a radiation energy density that's consistent with 3 neutrino energy flavors, but we don't really know that they're neutrinos. They could be something else. Once they detect the mass density background from neutrinos, they've proven that the neutrinos are there, but only in a bulk sense. You're talking about trying to catch them one by one. The Ptolemy experiment, so right now we're like 15 orders of magnitude away from success, and the Ptolemy experiment hopes to bring that much closer to success. I don't know if they can make it, but I think it's a very exciting step along the way.
Okay, thank you very much, John. I don't see any other questions, so let's move to the next speaker, Tamara Davis.
Thanks, bye-bye.
Yeah, thank you very much, John. That was great, absolutely fantastic talk. Okay. Tamara Davis, Cosmological Constraints on Fundamental Physics. So if you, very good. I'll give you a 5-minute warning. Okay.
Okay, awesome. Thank you. Hi, everybody. Yep, so my name's Tamara. I'm at the University of Queensland and I'm a cosmologist. So today I was going to talk about cosmology and how it can constrain fundamental physics. I noticed that a lot of people attending this conference are not cosmologists, so I've sort of aimed this talk mostly at the non-cosmologists amongst us, so that we can try and understand what the constraints are and how we can constrain fundamental physics with cosmology and what the constraints that we're producing actually mean. So I'm in Australia. One of the things we usually do at the beginning of our talks is just acknowledge the traditional owners of the lands on which we speak. So for here at the University of Queensland, that's the Turrbal and Yagara nations, and wanted to pay my respects to their elders, past, present, and future. The one thing that I thought I would mention from Aboriginal astronomy that I really, really love is that because in the Southern Hemisphere, we've got such a bright Milky Way because we're looking towards the center, they have some of their constellations that are made from the dark patches that go across the sky, as opposed to sort of the European tradition, at least, which is like making constellations out of the bright stars. And considering I talk a lot about dark matter and dark energy, I found that particularly poetic. So I love mentioning that part of Aboriginal astronomy. Okay, so one of the things that I want to mention right at the beginning of this talk is essentially just reminding us just how what a golden age of astronomy we live in, basically. We're seeing things like the cosmic microwave background, where we're basically seeing light from almost the beginning of time. We're routinely observing exploding stars. This little animation on the right is an animation that one of my students, Samuel Hinton, made of the dark energy survey supernovae that we're discovering. If you can see some sparkles going off in those galaxies, those thin pencil beams that we searched for. We're measuring hundreds of millions of galaxies. This map on the bottom left is one that the Dark Energy Survey released just a couple of weeks ago, showing the dark matter distribution using weak lensing of over 100 million galaxies. And we're detecting things like gravitational waves, let alone all of the cool neutrino stuff, etc., that we see before. And you're hearing people talk about, next generations of surveys, a few generations down the track, maybe, seeing every black hole merger in the entire observable universe and tracing every galaxy that we possibly can in the observable universe and the diffuse matter between them. So we're really in a golden age of data, and it just, makes it even more important to get the modeling right. So with that much data, you have some significant modeling challenges. But it means we can answer some fantastic questions. So, you know, we want to ask the little questions like, how did the universe begin? How do the laws of physics work? And how will the universe end? So more specifically, we really sort of, you know, what initiated the Big Bang? How were primordial fluctuations generated, the things that ended up forming the seeds of the galaxies, etc., that we see today? Is general relativity a correct theory of gravity, including the way we're implementing it? And how do gravity and quantum physics interact? I think this is one of the most interesting questions in physics at the moment. You know, what's our quantum theory of gravity? How do we get those two theories to play nice together? Are there any particles beyond the standard model of particle physics? And what are dark energy and dark matter? And for how the universe will end, if we've got everything else sorted, we still will need to know what the values of our constants of nature are and what parameters there are in our model, like densities and things, to understand, have any attempt to make a prediction of the future of how the universe might end. So what I'm going to talk about today is we've got a summary of where we're at, you know, concordance cosmology at the moment. Many observations agree, mostly with a few tensions. Is cosmology done? I'm going to argue no. Partly because of those tensions, partly because we still don't understand a lot of the things that we're observing. I'll classify the types of cosmological probes that we use into ones mostly that do expansion and others that do structure of the universe, and then go through some of the current constraints and recent results on those. And this plot at the bottom is one that came out a couple of weeks ago, showing one of the tensions with the local measurements of the expansion rate of the universe at the moment, disagreeing with the ones that came from structure, etc. So I'll talk about a little bit about that. So this is the picture of the universe that we know and love. Universe started radiation dominated. About 100,000 years after the Big Bang, matter radiation equality happened and matter started to dominate. A bit under 400,000 years later, we've got the surface of last scattering, and we see the cosmic microwave background coming from there. Then acceleration began about 7 billion years after the Big Bang, and shortly thereafter, not at the same time, but shortly thereafter, dark energy started to dominate the universe. And of course, the neutrino background that was just mentioned would be coming from before this surface of last scattering from the very early universe. It would be very cool if we could see that. Now, the kinds of observations that we use here, we've got things like nucleosynthesis, we've got sound horizon scale, both at the cosmic microwave background and in the galaxies. We've got the power spectrum of fluctuations we see, both in the cosmic microwave background and in the distribution of galaxies. We've got luminosity distances measured from things like supernovae and gravitational wave standard sirens. We've got angular diameter distances and direct measurements of the Hubble expansion rate at different redshifts, using things like baryon acoustic oscillations. We've got gravitational lensing, both weak and strong. We've got growth of structure, which can be measured both statistically and directly with peculiar velocities. And all of these have led us to the point where cosmology papers these days are quoting things to typically, or quite often, better than 1% precision. So this is from the Planck 2018 paper. And so we have the audacity now to claim that we can measure these cosmological parameters to quite a strong level of precision, while acknowledging all the time that these are model-dependent constraints. If you change the model, you get different values for these, somewhat slightly, depending on how much different freedom your model has. And typically your error bars go up when you add extra parameters, etc., like more species of neutrinos, for example. So with cosmology done, if we're quoting 1%, no, I don't think so. Mostly for a few reasons. Well, one's the extensions that we were just talking about. We need many different probes because they probe different things. So here is also from the Planck paper. You can see that in the space of measuring the equation of state of dark energy and how it changes with time, Planck is not very constraining alone and needs things like baryon acoustic oscillations and supernovae. The previous things I had there also had BAO in them, by the way. And also because there's some tensions, like some small maybe tensions within the CMB itself, where you've got the low multipoles, so the large scale things disagree slightly from the smaller scale things. And the one I just mentioned before, things like if you're measuring H0, the Hubble parameter, Hubble constant, the low redshift measurements like the supernovae seem to be somewhat in tension with higher redshift measurements like CMB and BAO, for example. So these are all things that we need to explain. And here was since you were talking about neutrino masses and constraining them using cosmology, these are other things that we would really like to actually nail down and measure properly. So when we're doing cosmology, I like to sort of make a clear distinction between two types of things. We've got homogeneous measurements, so measurements just of the homogeneous expansion rate of the universe and how that's changing. So the deceleration and acceleration of the universe. And then the other type are inhomogeneous measurements. So measurements of growth and structure. So how fast structures are growing, how big those structures are at different cosmic times. And these give you different constraints on the different models. So I'm going to use those symbols on the corner of my slides to sort of mark when I'm talking about a homogeneous constraint versus an inhomogeneous one. So the standard things that we use in cosmology, they're standard candles and standard rulers. Standard candles include things like supernovae and baryon acoustic and a gravitational wave, standard sirens. Standard rulers include things like the size of the fluctuations in the cosmic microwave background, as well as baryon acoustic oscillation. Standard rulers, the distribution of galaxies. And then there's other things that are like the time delay that people have been able to measure between strong lensing and seeing light that's traveled different paths to get to us and measuring the different time delays that you get from these. And so these are also measures of expansion. A lot of people actually sometimes ask where exactly these baryon acoustic oscillations come from. So I thought I'd just mention quickly that the baryon acoustic oscillations arise from fluctuations in the early universe that then you have sound waves travel. So it's literally acoustic oscillations that cause overlapping patterns in the background. And the peak of those patterns is where galaxies form. And so if you look at the distribution of galaxies at the present day, the distribution has this characteristic scale of how far a sound wave could travel before the universe became too dilute for sound to travel anymore. And that was approximately at the surface of last scattering, but it's a little bit later at the drag epoch because there was enough photons to push the sound waves even after most photons could free stream throughout the universe. And we quantify that using things like power spectra and correlation functions, like the kinds that you will see with baryon acoustic oscillation peak. Sorry to everyone for whom that was a very simple vision. But distances have a limit, and it doesn't matter how well we measure them. The limit arises because some models can't be distinguished using only distance data. So this is a really old paper that I wrote now, but this was one of the points of this paper was testing all sorts of different cosmological models against supernova data. And the long story short of this was that many models could agree perfectly on the expansion history of the universe. And therefore, you can't use the expansion history to figure out which of those models is correct. They disagree, however, on other aspects of the universe, for example, how things cluster. So we have to move to other measurements beyond just expansion to be able to figure out which model is the correct cosmological model. You want to really go beyond the standard model of physics. So what kind of other measurements do we do? So what kind of things do we look for? Other things that we look for include deviations from general relativity. So in the metric, the factors that go in front of the time components versus the factors that go in front of the spatial components are the same in general relativity, but not necessarily in general. And for something like galaxy clustering is sensitive to the spatial prefactors, whereas something like gravitational lensing, which involves light traveling through space-time, is sensitive to both the temporal and spatial components. So we can compare results from clustering to results from lensing and see if we can distinguish these kinds of different models. Another thing that we measure a lot is the rate of growth of structure. So if you have a galaxy cluster, if we've measured redshifts to all of the galaxies, the ones on the close side of us that are falling towards the center of the cluster will have an excess redshift away from us. So they'll look a bit further than they should compared to where their redshift should have put them. Whereas ones on the other side that are falling towards us will have a bit of a blue shift, an extra movement towards us that they wouldn't have had just due to the expansion of the universe. And that makes clusters look compressed in redshift space along the line of sight compared to their size horizontally. And so the same galaxy surveys that we can use to measure baryon acoustic oscillations can use to measure growth of structure. And the parameter that we use here is often F, and it's the rate of change of the overdensity with respect to scale factor done logarithmically. And it's generally approximately dependent on the matter density, but to a different power depending on which cosmological model you're in. So this power is one of the things that we try to measure. The amplitude of density fluctuations, for people not in cosmology, this one can sometimes be very obscure. So just to make it a simple explanation of what this actually is, if you just go somewhere in the universe, draw a sphere with 8 megaparsec radius, calculate its density. Go somewhere else, do another sphere with 8 megaparsec radius, calculate its density. Repeat many times, calculate the dispersion in your measurement, that's sigma rate. So we're looking at how, what are the deviations from the mean density of the universe in that particular size? And people ask why 8 megaparsecs? Well, when it was first measured, 8 megaparsecs was about the level where the answer was 1 when you're using normalized density units, but relative to the divided by the mean density. And so that 8 is just arbitrarily, it was about 1. We think it's more like about 0.8 these days, but it's close. You'll often see this S8 used these days instead of sigma rate. And you'll often use F sigma rate used because different constraints have different degeneracies. So sometimes you can't distinguish between the growth of structure and sigma rate. They're very degenerate. And in things like the weak lensing measurements, here's an example from the kids survey from Hyman's et al. And if you look at this pink contour, which is the cosmic shear measurements, so the weak lensing measurements in the omega m and sigma 8 plane, you can't really make a distinction between them, but you can, if you draw a line along this degeneracy direction, you can constrain the width of that very well. And so this is basically constraining the width of this band here. So that's why that's used. Of course, other things that we want to measure, things like non-Gaussianity. We want to see if there's any skewness in the density distribution. So a positive FNL means that you've got more clustered clusters than voids, and vice versa if you have a negative one. We can measure things like peculiar velocities and see if they compare with the predictions that we expect. So this is how fast clusters moving and how fast are things moving towards clusters. And then also things like the integrated Sachs-Wolf effect, which is, I think, awesome and really cool thing that you can measure from the cosmic microwave background. Because if you're in a universe with a varying background density, the photons that fall into a gravitational well can climb out of a weaker gravitational well, for example, if there's dark energy, and therefore you get blue shifted photons around a cluster. If they've passed through a cluster. So I wanted to remind people that there was actually hints of the dark energy around well before the supernovae showed that claim. And this, you can see this paper from 1990 and this paper from 1995. They were both using galaxy number counts and clustering type of measurements to show that dark energy should be out there. This in a way is a clustering measurement. I've got both colors on the corners because it's a clustering measurement, but it's also a homogeneous one because the solution to this is having the denominator. Like if you look at how many galaxies there are as a volume, the denominator is like a ruler because it's a volume. And that's the thing that changed if you had a cosmological constant, which made the number density as a function of redshift consistent. But both these papers claimed that we should have an 80% of the critical density in cosmological constant if we wanted to explain these number counts. Of course, it wasn't really super confirmed, or at least believed, until the supernovae gave this strong evidence. And I thought I'd just show a couple of contour plots. We'll go through a contour plot movie now of some of the advancements that have been made. So here's some of the original supernovae data from 98, 99, and the contours in the matter density and cosmological constant plane that they had. Here's some of the more recent supernova data, where the red one is the data from the Pantheon survey, so 1 and 2 sigma contours. So you can see we've zeroed in on this one quite a lot these days. And one of the things that we're working on at the moment is one of the things I'm helping out with a bit here is the dark energy survey. So far, we've only done a spectroscopic sample, which is just over 200 supernovae, but we've got a couple of thousand that we're hoping to get out pretty soon. So that will shrink these contours even further. So those were standard candles, some standard ruler measurements. Obviously is the cosmic microwave background. And this is such a sensitive probe. It measures both the ruler and the clustering, but this is a kind of plot that, yeah, the way I'm going to show this can be slightly misleading, but just to show you how sensitive the CMB is to some things like dark matter and dark energy is if you keep all of the parameters the same and just change the dark energy, that's what it, just remove dark energy, that's what this would look like approximately. And similarly with dark matter. So of course, if you not only change the dark energy and dark matter, but change other things, you can get it back to looking much more like this because there's some degeneracies, but it is an incredibly sensitive probe. The acoustic peak detections in the baryon acoustic oscillations also have made incredible advances over the last decade and a half. So this was the Sloan Digital Sky Survey from 2005. This was the Wiggle survey, which I was involved in 2011. Some of the BOSS stuff from 2013, and then I'm just sort of going through in movie style on here, not getting you to absorb these, but here's some of the acoustic peak measurements that have been made that were released by EBOS just this year. So incredible advance in how much we've been able to measure and at what different redshifts. And these BAO measurements also can get put on a plot similar to this. That's the sort of slice through that we would have done with the Wiggle survey a decade ago now. EBOS's results, I think that's a 2020, so late last year, are very small contours in this plane now. And the DESI prediction, so DESI is the dark energy spectroscopic instrument, which is the prediction from this, which it's just started main observations and will go for 5 years, should be able to zoom in to this sort of level on this type of diagram. But as I mentioned before, that's not enough because even if we can hammer in on those particular parameters really, really well, doesn't tell us enough about all of the other parameters in order to be able to nail down what the cosmological model actually is. I think I've actually said most of this, but baryon acoustic oscillations can be interesting because they can be applied both radially to give a measurement of h as a function of z, because that's dependent on distance. This is the Hubble parameter. And tangentially to give angular diameter distances, and the same measurements that do BAO are sensitive to growth. So I think I've said most of that. So the last thing I wanted to mention is some of the results that have come out quite recently, and the things that are being done by things like, this was from HyperSupremeCam, the KIDS survey, and the Dark Energy survey, where now we've got contour plots of the matter density on the horizontal axis and this S8 parameter on the vertical axis. Here, the top one on HSC is sigma 8 and then S8, and you can see that sigma 8 has this big degeneracy direction and S8 is much less degenerate, which is why it's used. So how are these ones being done? So let's just talk about these lensing and clustering results, because there's a lot more of these going to be coming out soon as well. So strong lensing is the type of thing lensing that most people are more familiar with. And that's when you get multiple images of the same background source by light that has traveled different routes through space to reach us here on Earth. And usually that's associated with a big galaxy cluster or something like that along the line of sight. And that leaves these amazing images where you have a cluster of galaxies in the foreground with these arcs in the background of the lensed galaxy. And the key thing here is that if there is a overdensity in the foreground, then the background galaxies will tend to line up in circles around that foreground galaxy. And it can be used to make very sensitive, detailed maps of the foreground galaxy distribution that's been like the one that's been done here. Now, for weak lensing, that's different. You don't get double images of the same galaxies. You just get the statistical distribution of shapes of galaxies in the background of the general matter distribution that all of the light in the universe has to pass through. So every line of sight has some level of lensing associated with it. And by observing many, many background galaxies, you can statistically use the shapes of those background galaxies to measure the distribution of density along the line of sight from them. So you want many, many background galaxies and also at many different redshifts in order to be able to map that background distribution or that foreground distribution really well. So here's what's now the old map of dark matter that was made using this technique by the Dark Energy Survey in 2017. I'm a member of the Dark Energy Survey, but I am not one of the people that's doing this kind of measurement. And I love the scale of this map. You know, it's a billion light years across there. Is just really cool to think of the scale on which these are working. And this was a similar map from the kids team, the kilodegree survey, where you've got overdensities and underdensities in these sort of hot and cold spots. It looks a bit like the cosmic microwave background projections. And this one is the new map of dark matter that was just released a couple of weeks ago from the Dark Energy Survey. And this one is superimposed on the full sky picture, just to give you a sense of scale of how big this map is on the sky. And this is the Milky Way, of course, whoops, going across here. Now, maps are pretty, but they don't give you quantitative information about what the parameters of the universe are. So how do we use these kind of maps in order to quantitatively go for the parameters of the universe? So you may have encountered something called 3 times 2 point. What is that? That's 3 2-point correlations calculated simultaneously. So here you've got your telescope, here you've got your set of galaxies in the foreground and some galaxies whose shapes you've measured in the background. You've got usually photometric redshifts, sometimes spectroscopic redshifts to the galaxies in the foreground, and you've also got photometric and sometimes spectroscopic redshifts to the galaxies in the background, but let's assume it's mostly just done with photometric redshifts. Then you take these and you look at the correlation function just galaxy to galaxy in the foreground. You get the correlate, that's one 2-point correlation function. The second 2-point correlation function is between the galaxies in the foreground and the lenses in the background. Obviously, the shapes of the galaxies in the background should correlate with whether there's an overdensity in the foreground or not. So this is the second correlation you get. And the third is the correlation between the shapes of the galaxies themselves. And that's the lensed galaxy there. So these done simultaneously is what's known as the 3 by 2 point measurement. And that's what you saw in the previous plot. On the left here is some of those measurements overplotted. These are not combined. The Dark Energy Survey one is this gray one in the center here. And if you combine, now on the right, so this here on the left is in the matter density S8 plane, and on the right is in the Hubble parameter omega m plane. And you can see here one of those clear things, which is one of the reasons why cosmology isn't finished, that we're getting some tensions between things like the Hubble parameter measured with these local supernovae and Cepheid variable calibrated distance ladder. And some of these other measurements that you're seeing here. So the blue small contour down here is the Dark Energy Survey stuff combined with the external probes that were consistent with it. Cool. So basically, mainly what I wanted to get across in this talk was all of the many different ways in which we can constrain fundamental physics with cosmology. I didn't get through anywhere near all of them, but these two questions are two that are big on my mind. And these are some of the pieces of evidence that we have for those. And without going through them, I think I will leave it there and see if there's any questions.
Okay, thank you very much. Those were the animations and everything. Beautiful, absolutely gorgeous. We have a question. I don't know if you can read it.
We've learned a lot from CMBR. Any chance to measure CNU? I think that was John. I already answered that one at the end of the previous talk.
Okay, so then I have my own then. There is this idea you need dark matter to become the seed for the galaxies to form. What is the probability that we would have a galaxy without dark matter?
That's actually one of my favorite pieces of evidence that dark matter exists. And I think I'll put it here at the bottom of this left-hand evidence column. Big stuff exists is one evidence for dark matter, because if you look at the time before the cosmic microwave background, because if we only had baryonic matter, the pressure support meant that large structures couldn't collapse very early on in the universe until after that pressure support disappeared, after last scattering or after the drag epoch. And if you look at the size of the fluctuations in the cosmic microwave background at that point and calculate how long it would take for a galaxy to form from a fluctuation of that cosmic microwave background size, there's just not enough time in standard gravity to get from that point to having the big galaxies that we see at the present day. And so the fact that dark matter could have collapsed well before the cosmic microwave background was emitted and formed large overdensities before then is one of the reasons that we can have really big structures at the present day. So I think that that's really strong evidence that dark matter of some sort is out there, something that's pressureless.
Great. So you don't expect any galaxies without dark matter? Is that what you're saying? Pretty
much, yes. I mean, you can have, so most galaxies should be associated with dark matter halos. Note that at the point of the, when the sound horizon stopped, you would have had overdensities that were primarily baryonic, because they were the sound wave overdensities. So you had some dark matter overdensities, but then you had these other overdensities that were primarily baryonic. But those should attract dark matter to them, as well as the dark matter attracting baryonic matter to it. And so that should equilibrate relatively soon, but there was a slight difference, and the formation of that was different in the early times.
Great. We have a question. It's a little long one. Do you mind reading it? Yeah.
Yes. So it says that it's clear that one's assuming the cosmological principle. And true, I've got another. I don't think I have the slide here, but we actually made some measurements of the homogeneity of the universe, and using these this was with the Wiggle survey, used the distribution of galaxies in the universe to see where we hit homogeneity at what scale, and we estimated that to be at about 100 H inverse megaparsecs. But I'll continue your question. It's clear that one's assuming the cosmological principle. There's a persistent discrepancy between the cosmic radio dipole with the CMB dipole, stretching back at least a decade, that's recently been extended to quasars. Taking it at face value, this implies a special direction. Interestingly, one finds that the largest values of H0 within lambda CDM across strongly lensed quasars, Pantheon, and attempts to use quasars as standard candles are in the hemisphere aligned with the CMB dipole. Early days, but could Friedman, Lemaitre, Robertson, Walker be under a little pressure? I think that so basically this could inhomogeneities in the universe be causing for example, the tension between low and high redshift is, I think, much of the essence of that question, and also this dipole effect. There's not massive, I think that that's one of the things that really has to be looked into carefully, because I think if we do find ourselves in a slightly special place in the universe, then that can cause discrepancies in the model. And that while there's been plenty of papers out showing that there's no evidence that that exists in the supernova data, for example, it's not completely ruled out yet in my mind as a possibility. So,
we have time, so you can read this. Yeah.
This is an isotropy question, not a homogeneity question. Okay, so we're asking whether it's different in different directions, not in different positions, because you would specifically like to know about isotropy rather than homogeneity. One of the other persistent things that has been seen are large-scale bulk flows. On the bulk flows remain large at large scales. You actually expect bulk flows on large scales in normal lambda CDM because the modes that create bulk motion are actually larger than the kind that you expect to influence clustering. But nevertheless, there is still some evidence that these bulk flows are larger than predicted in lambda CDM. One particular direction could be an effect there as well. So yeah, I think inhomogeneities and anisotropies are things that we still do have to investigate.
Right. So we have another question, or it's the same person? So
yeah.
Okay. The dark matter clamps together, right? And does the dark energy do that as well?
That's one of the things that we're trying to measure precisely with things like the dark energy survey. Is there any evidence for dark energy clustering at all? So far, it seems perfectly consistent with just a equation, a cosmological constant, an equation of state of dark energy of -1, which doesn't cluster, is just smoothly distributed throughout the universe. So there's no evidence yet that it deviates from that. So at the moment, something like vacuum energy, if we could explain the magnitude of it, is still the leading candidate for dark energy, I would say.
Okay, very good. Thank you very much. The pictures and the simulations were absolutely amazing. Thank you very much. It really gives a clear picture of the universe. Yeah. Again, thank you very much, and for your introduction as well. That was an interesting slide. Yes.
So thank you very much for having me.
Thank you, Tamara. Okay. Okay. So we'll move on to the last talk of the session. Peter.
All right. Perfect. Can you see my screen?
Yes, charged particles for dark matter detection. Peter Graham from Stanford. Peter.
Perfect. Thank you so much.
You have time, Peter. Don't rush it.
Okay. Great. Thank you so much for inviting me. Sorry I couldn't be there in person. I should say also, I'm happy to be interrupted with questions. I don't think I would notice the chat, but Giannis, if you let me know if there's someone raising a hand or something, that would be great.
Definitely, yeah.
Okay, and let's see, hopefully you can see my cursor, I don't know. So I actually wanted to talk about perfect. I wanted to talk about two sort of separate topics. The first is something we're actually finishing right now, which is a new way to look for dark matter, in particular millicharged particle dark matter, with the trapped ions as a detector. And then the second topic is something that's already appeared, is a way to look for axion and other ultralight dark matter with charged particles like protons in storage rings. Okay, so let me first talk about our new idea for looking for millicharge particles. And I should say this is with my collaborators here, and we're especially grateful to our experimental colleagues for, I should say, I'm really a high energy theorist, but I'm definitely very grateful to our experimental colleagues for keeping us kind of grounded in what could possibly be done with this technology. This should appear as a paper, hopefully in the next few weeks, we'll see. So to begin with, I can say, why should we look for millicharge particles? There's actually been a lot of interest in that recently, so I'm really not going to try to recap the many, many papers that have come out recently. By millicharge particle, I really just mean some new particle of some mass, I don't know what it is, but with electromagnetic charge, which is some small number epsilon times the fundamental charge E, okay? And so from now on, I'll refer to epsilon as the charge of the millicharge particle that I'm looking for. And you should think this could be, you know, a tenth, 100th, a millionth, and so on. In general, there's been a lot of interest in these. I think it began even a long time ago. People have talked about millicharge particles for a long time because we have this mystery of why charges in our universe are quantized that we've never really explained. But more recently, also, people have thought seriously about millicharge particles as a possible dark matter candidate. It's been even discussed in the context of the EDGES result and so on. So I really won't go too much into why you'd want to look for these. I think there's been a lot of interest in it, but let me just kind of jump into our idea, how we think you can go after it. Let me begin actually by talking about, of course, normal dark matter detection. The way we normally think about directly detecting some dark matter particle is, okay, it's very weakly coupled. It passes right through the Earth, and it comes to some deep underground detector. And then if we're lucky, we get a few hits. The dark matter strikes some nucleus or an electron in that deep underground detector. And of course, there have been a lot of great experiments looking for that, and they've really pushed down the limits on such particles. So here you see from this nice paper an example. This is the cross section for dark matter striking electrons versus the mass of the dark matter, and you get some exclusion region like this in this cross section versus mass plane. But this isn't the whole story. In particular, I'll be interested in the possibility that the particles might actually be much more strongly coupled to the standard model than these extremely weakly interacting particles that are often looked for. And that's because these millicharge particles would generically or could generically have very large couplings to the standard model. If the charge is 100th or 1000th, that's a small charge, but electromagnetism is so strong, it's still a very strong coupling for a new particle to have. And you can see that generically, even not just talking about millicharge particles, if the particle has a stronger coupling to the standard model, these exclusion limits have tops to them because the dark matter particles wouldn't even make it through the Earth. They couldn't even make it through all the rock and all the shielding to get to the detector. They would get stopped first. In fact, they don't actually get stopped. Instead, in particular, let me start talking specifically about millicharge particles. In the whole parameter space that I'll show you in a second that I'll be interested in, they do have very strong couplings. And as was nicely pointed out by these really nice papers here, they don't just stop in the rock. In fact, they scatter off it and they thermalize, and they reach this room temperature or the ambient temperature of the Earth, and then they just start diffusing around. This is relevant, so they could still make it to the detector, but this is relevant because then they'll have energies that are around room temperature, around, let's say, 30 millieV, which is far below the thresholds for most of these direct detection experiments like LZ or CDMS or anything like that, which generically have thresholds around keV, and if people work really hard to try to push those thresholds all the way down to maybe electron volt or something. But it would be very difficult to look for a millicharge particle that had only about 30 millieV of energy to possibly deposit in your detector, even if you had a sensitive enough detector and things like that. However, you'll notice that because these millicharge particles, if they are some component of the dark matter, are always raining down on the Earth, then once they get stopped and start diffusing in the rock, they would actually generically pile up to very large densities, what I think these authors referred to as a traffic jam, meaning you actually could have around some detector on the Earth a very large number of these particles. In fact, if they exist, even as a small, very small fraction of dark matter, we'd be surrounded by some dilute kind of room temperature gas of these particles at all times, and it would be filling our experiments and things like that. But it's sort of fascinating to think that simply because they're at too low in energy, we wouldn't have seen them in any of our biggest dark matter detection experiments so far. So then the question is, how do we go looking for this? What have we got? Well, these millicharged particles, it's sort of interesting. They're all around us. They've got relatively very large number densities compared to normal dark matter candidates that we're used to looking for. And also very large scattering cross sections off of standard model particles. So those two things seem like wins. It seemed like we should be able to detect it. But of course, they have such low energies that we know we're going to need a very low threshold detector, a detector that's very sensitive to even very small energy depositions. Since we have such a large density and large cross section, though, we can kind of trade off. It's hard to make the normal larger WIMP detectors, with such a low threshold. We can trade off, we can accept a low target mass if we can have this low energy threshold for the detector. And of course, since these millicharged particles interact via electromagnetism, we really want to maximize, we want some detector that really maximizes this charged particle scattering. So all of that led us to propose that we can use trapped ions, a technology that people have already played with now for many decades and even worked on perfecting for a long time. They may be really kind of optimal detectors for these millicharged particles. How would that work? So let me show you my sort of crude theorist cartoon. So imagine I have some ion in a trap here inside my experimental apparatus, inside my shields. If a millicharged particle comes in, it would start heading toward the trap. Of course, I said they have large scattering cross sections. Generically, over a very wide region of parameter space, these millicharged particles actually scatter quite quickly. And so, in fact, they would generically diffuse around inside the shielding, around the trapped ion. But eventually, you should imagine all the materials around us, all the space around us is filling with the gas of these millicharged particles. Eventually, they'll wander into the trap, and they may pass through and strike the ion that's trapped. And so you have this this energy transfer mechanism from the walls of the device, the walls of the experiment, to the ion that's trapped in the center. These ambient millicharged particles can't be shielded. They will always make their way in, and they will transfer some energy and heat the trapped ion. And so you can see here that's our generic signal that we want to look for is the heating rate. Don't worry too much about the whole details of this formula. I should say this is actually not even the real signal we use. This is more for illustration. We're looking for the heating rate of this ion. This is the heating rate if there was no energy threshold at all. There is actually an energy threshold, so the real formula is a little more complicated than this, but you can already learn a lot just by staring at this. We see first we expect that the heating rate is proportional to the temperature of the millicharged particles as they enter the trap, minus how far above they are above the temperature of the trapped ion itself. And then also, if you're careful, you can stare at this formula and read off the shape of the regions we're going to be sensitive to in the mass parameter space, mass and charge parameter space that I'll show you in the next few slides. So these can be read off of this formula. You can see from this that I need the ion to be quite cold, or I won't have a heating rate. I need the ion to be much colder than the environment. That's kind of the main point we're living off of here. That is, of course, how ion trapping works. You needed that was how people built ion traps anyway, to cool and hold on to the ion. The ions are generically much colder than room temperature. I don't need the trap to be cryogenic. It can be room temperature, and we'll use some of the room temperature traps. However, if the trap is cryogenic, if these walls are also cooled, then that actually has real bonuses, although you can see that reduces the temperature of the millicharged particle. In fact, it turns out that because the millicharged particles thermalize to the energy, to the temperature of the walls of the trap, they slow way down as they enter this cooled region, if it's cryogenic. And since in equilibrium, the flux leaving the region needs to be equal to the flux entering, and the millicharged particles are so much faster outside, you can see they pick up a much larger density inside. So in fact, just by making a cold experiment, you've immediately enhanced the number density of the millicharged particles inside the trap even further. And you've also taken advantage of a nice property of charged particle scattering, and this Coulomb scattering. the slower the milled-charged particle is going, the larger is its Coulomb scattering cross-section off of this charged ion. So we'll see that the cryogenic ion traps can even have sort of a extra advantage in certain parts of parameter space. Okay, so that's the basic idea of how we would use an ion trap to go looking for these milled-charged particles. We look for this ambient heating rate that's caused by the milled-charged particles constantly leaking in and heating the ion. Why should ion traps, though, be sensitive enough? Why are they actually good detectors for this? The reason is essentially that people have worked for so many years at making ion traps, have excellent isolations. The ion is very well isolated from the environment. And in fact, therefore, you can see very low energy depositions. The ion is a very sensitive probe to even a small energy deposition into the ion. Of course, people have done this for a long time, but there's been I would say, a burst of activity in recent years motivated by quantum computing, by the fact that ions and traps, charged ions, are a serious technology of interest for people trying to build qubits and quantum computers. So we'll take advantage of that. Let me just mention a couple experiments. First, the base experiment at CERN, which trapped a single antiproton in a Penning trap. You can see there, these are their results here. This is the heating rate of the trapped antiproton. And all these different colored dots are different experiments, but this base experiment, the measurement they took is this blue dot here. And you can see they're sensitive to something like 10 to the minus 12 EV per second heating rate. Some extremely low heating rate they can see. That right there tells you why we were interested in ion traps as detectors of dark matter, because they can in fact be very sensitive detectors. And also, as I'll show you in just the next slide, they're sensitive to single energy depositions all the way down to about nano EV or so. This one wasn't directly motivated by quantum computing, but as I mentioned, there are many experiments motivated also by quantum computing goals. So for example, you can trap positively charged ions. Calcium-40 is a prime example. This shows, again, this plot shows the heating rate for many different experiments. Each of these dots is a different ion trap. And you can see that there's been a lot of progress made over the years. They've been able to really improve the sensitivity and reduce the background heating rate in these traps down to very low levels. These ion traps are getting down to nano EV per second or so heating rates. So this is really why we think ion traps are very exciting as probes of this kind of dark matter. There are, as I just showed you in the previous slide, there are many different ion trap experiments. We chose 3 that we think are very interesting and representative of this. And you took the results, the previous results from past years from those 3, and we were able to reinterpret them to immediately set new experimental limits on milled-charged particle parameter space, as I'll show you, many orders of magnitude past what had been done before. Although I did want to point out that these 3 were chosen in a sense somewhat randomly. I mean, they were chosen to have good heating rates and things like that. But actually, there are many more experiments, and I think it would be very interesting. I think looking at those experiments, reinterpreting old results, and also interpreting new ion trap results, that could really extend the reach of these experiments and might even provide a positive signal. We looked at these 3 traps. I show here the different types of traps, either the RF, Paul trap, or Penning trap, and the particular ions that were trapped to show you the kind of the variety of experiments available. One thing to focus on, you'll notice these first 2 experiments are room temperature experiments, while the third, this base experiment, is a cryogenic experiment. This column here shows you effectively the threshold of the experiment. Each of these ions, when it's trapped, is trapped in essentially parabolic potential or pseudopotential. And this energy scale here is actually the energy splitting between the different states in the simple harmonic oscillator. So of course, if I deposit much less energy than this, I can't even get the ion to hop up 1 energy level in the trap. So that's I can't see it. That's a threshold for the detector. But you'll notice these thresholds are in the nano EV or so, or even less. That's what makes us very optimistic that this is a very different kind of dark matter detector than something like LZ or CDMS or something. And you can be sensitive to such low energy depositions. That's, of course, why you could even dream of doing detection with just a single ion or a few ions. This column here shows you the temperature of the ion in the trap. Sorry, I think I changed notation. This is what I called T ion on the previous slide. And again, you can see the ion is cooled far below, even in the cryogenic experiment, cooled far below the ambient temperature of the experiment in the room. And this shows you what impressive heating rates they've achieved in these traps, getting down even to small fractions of a nano EV per second sensitivity. Okay, so using these traps, we can then calculate the density of millicharged particles coming in, and therefore the heating rate of this ambient gas of millicharged particles. And when we do that, we find we can set these new experimental limits. And this plane, for example, is the number density of these millicharged particles versus epsilon, their charge. Just to orient you here, these gray bounds are previous bounds from LEP, for example, the collider looking for new particles of a certain charge. Colliders, of course, can only look down to a charge of about 1/10 or so. Or oil drop experiments, or also more recently, people performed a series of optical levitation of dielectric spheres, looking again to see if they could detect some evidence of some new fractionally charged particle. We were excited to see that these ion traps could really set orders of magnitude improved limits just by the heating rates that were observed, from past experiments. Not these experiments were not done with the goal of dark matter detection at all. They were sometimes even just done with the goal of quantum information, but nevertheless, they're already setting limits on new fractionally charged particles. If I move instead and plot this in this other plane of the charge of the particle versus the mass of the particle, the mass of the new particle, you can see these are bounds from supernovae and from colliders, and this N effective is a bound from cosmology. And these set strong bounds on light millicharged particles, but of course it's very difficult for these kind of probes to reach very high masses. Whereas interestingly, these are the new bounds that we would set with ion traps, and they can cover, you can see, orders of magnitude in both mass and charge, far beyond what previous experiments are able to probe looking for millicharged particles. And one thing I like that I kind of wanted to point out about this plot is you can see how different the different kinds of ion traps are. They cover really different and very complementary regions in this plane. That's because of these differences I pointed out. They have big differences in the energy threshold, big differences in the type of particle, whether it's calcium or beryllium or a single antiproton. So in the mass of the target that's being struck, that changes the kinematics and changes the rate for millicharged particle scattering. They have differences in what heating rate they were able to achieve and the temperature, for example, of both the ion and the experiment itself. And so all those differences mean different ion traps, all the different work that's been done by the different ion trapping groups kind of all around the world really is very useful. They're all very complementary and helps us cover a large chunk of this millicharged particle parameter space. Okay, so these are the current limits we can set. However, I did want to point out that we think this is the current limits were set even with existing experiments. But if you specifically designed a search with one of these ion traps to look for dark matter, you could even do significantly better. So this is in the same plane again, and this brown region now is kind of the union of all those experimental limits that we are setting with current results. But now we drew some lines to guess how good you could do with a dedicated ion trap. And in particular, you can see that there are many possible ways to improve on the previous experiments that were done without dark matter in mind. For one thing, I described our signal as looking for a heating rate, which is what we can do so far with the data that's available. But in fact, with a dedicated search, we know that, for example, LZ or CDMS doesn't look for the heating rate of their whole bulk material. They look for the individual event spectrum. If you, again, recorded individual events, the heating of this ion, they say at one time it jumped up 1 energy level, the next time it jumped up 5 energy levels in the trap, and so on, you could immediately significantly reduce the heating rate backgrounds and tailor your search specifically for dark matter. This would require a dedicated search because you require continuous monitoring of the ion, which is already used in some experiments, but not all of them. And then you can do things like, for example, making a highly charged ion. This is something that the field has been playing around with a lot recently. This blue curve shows, for example, if you, instead of used a singly charged calcium ion, if you had a charge 20 calcium ion, which you can make, how much better you can do. You really significantly boost the scattering of these millicharged particles. Or if you can drop the threshold. So for example, this kind of greenish curve here shows if we can use that omega minus mode that I had on a couple slides ago, which is an even lower energy threshold, if we can use that mode of the trap and observe it, then we can even further significantly improve reach into this plane and maybe even detect a millicharged particle. And in fact, something else that's being actively worked on in the ion trapping community is looking for collective excitations in these ion crystals, which might also significantly reduce backgrounds. Okay, so that was mainly what I wanted to say about ion trapping. If there aren't any questions on that, let me just look.
Peter, if you don't mind a question on that, would a microwave cavity give any signal? I mean, we cool them down and they have big volume.
Actually, that's a great question, and let me not really try to answer it except to say yes, in principle it could. We as you know, the frequency, the signal is crucial there for the microwave cavity, and dominantly the frequency would probably be a bit of a mismatch because the millicharged particle is moving very slowly. You know, essentially, as you know, the microwave cavity is looking for something that's at the speed of light, or is looking for something whose frequency is equal to is matched to the wavelength of the cavity. That said, though, the microwave cavities are, however, very sensitive. So I don't want to dismiss it. Actually, that's a really interesting idea. I think we should chat about that more after the talk. I like it.
Great. There is a question on the chat. Can you read it, maybe?
Oh, perfect. Yes, I see it now. Thank you. It says, so the question says, are you assuming both positive and negative millicharged particles? That's a great question. Thank you. And I didn't say, but that's very important. And then the question says, if so, could annihilation of photons be relevant because of the large density? The cross-section is suppressed by epsilon squared, so might be totally relevant for the parameters of interest, but absolutely right. That's a very good question. So we're actually, I didn't say it, but we're actually mainly assuming positive millicharged particles. The reason is that, although if the negatives were around, as you point out, there could be more signals as well. First of all, they could scatter as well, no problem. And then you might even have other kinds of signals like annihilation signals, which would be really interesting. Yeah, that's a great thought. We were worried about trying to assume that the negative millicharged particles would be around, though, because they would generically bind quite deeply over most of our parameter space to nucleons. The positive millicharges could try to bind to electrons, but if you look at it over our whole parameter space, the binding is very weak, so they would easily get knocked off of electrons. But the negative millicharges seem like they could well get stuck, even when they first scatter in the atmosphere or something in nuclei. There might be smart ways to look for it with that, but we kind of stayed conservative. Hopefully that answered the question. But I should say it's an interesting question, and that's certainly worth thinking about exactly what happens to the negative millicharges. We were sort of agnostic and said, let's conservatively just look for the positive ones. But
great. Just to follow up, the G-2 of the electron, there is something there. Could you tell, I mean, would that contribute to G-2 of the electron enough to be seen?
Oh, millicharged particles, you mean?
Right.
In principle, one could, but I believe those contributions have been calculated, and because we're at pretty low epsilon and you have to go through multiple loops, I believe that's small, but I could try to find the exact numbers for you after the talk.
Right. Okay, thank you. And there is one more.
Oh, great, yes. Oh, good. What is the main background? Actually, that's a great question. Thank you. Something else I should have said, but I didn't have much time. The main background, let me actually go back if I can, sorry, if I can figure out how to do this here. There we go. In fact, let me go back here. These are the observed heating rates in these traps that we used, and we just said, look, if the millicharged particle would have given a heating rate bigger than this, it's ruled out. We would have seen it in these traps. But I exactly skipped this great question you're asking, which is, where do these numbers come from? What is actually this is actually observed heating rates. This is not a limit. Okay, they saw the ion heating with this rate, and what is causing it? We worked with and talked with a bunch of these experimentalists. I would say the dominant thing is they want to cautiously say they're not 100% sure what the heating rate is. Actually, as you can kind of see from this previous slide, reducing the heating rate has been a major focus of experimental effort. I would say, and there are many different kinds of traps, so the answer may be different depending on the traps, but let me just give you a few examples. A lot of the reason they're actually plotting it versus trap size on the x-axis or electrode ion distance is a lot of times they suspect, and in fact in previous traps almost certainly was the case, that the heating was dominantly coming from the electrodes and electromagnetic fields that were holding the ion itself, right? Because you need reasonably strong electromagnetic fields to trap the ion anyway. You could see noise on that could heat the ion as well. However, I think talking with at least some of the people who've made several of these measurements, they're not 100% sure what their residual heating is coming from. In fact, that's an active area of research, is how they reduce that. So then that's kind of why actually I went on to say, so we think it's from the ions, but it could be from other sources. By the way, you can calculate whether it's from the imperfect vacuum in the trap, and that in many cases doesn't appear to be a problem, or at least for many of the traps, the vacuums are very good and shouldn't be causing this heating rate. But that was part of why for the future, I was actually focusing on this idea of observing individual events. Because while I suspect they will be able to reduce heating rates, since we don't know exactly what's causing the heating right now, we weren't assuming it. But if you can look for individual events, that's something different than what they've been looking for. The Coulomb scattering actually generally gives very high energy events. You can get around backgrounds that way. Perfect. Yeah, those are great questions. Thank you very much. All right. Were there any more questions, or I should go on maybe to? All right.
No, that's it. Okay.
Okay. All right. So since now I am running short of time, so let me kind of go through this second topic I want to discuss. This is work that has come out already, has appeared already on the archive and in PRD. And again, I wanted to thank my experimental colleagues, including Giannis, at least, who's on the call today. So the idea was how to look for axion dark matter and dark energy, in fact, using storage rings. And again, here we're deeply indebted to the experimentalists who were sort of crucial in knowing how to actually do this. So let me just kind of give you the basic idea, which is, so I say I want to look for axion dark matter or dark energy. Kind of what's the picture? What am I looking for? The axion would be a very light dark matter particle, and so if it is dark matter, it would have a very high number density. In fact, a very high phase space occupancy, meaning you can really think of it more like a homogeneous, kind of slowly oscillating scalar field in the galaxy. So it's oscillating back and forth in its potential here, and essentially think of it as some background scalar field filling space, filling our experiment. That looks like this, that's oscillating with a frequency equal to its mass. I'm interested in dark energy too, though. That's a very fascinating subject. And if it's anything other than a cosmological constant, then it too would have to be some sort, in other words, if it has some dynamics, if it's something other than a pure constant, it would have to be a scalar field in field theory. What would it look like? Well, we know, of course, from in fact, like the very nice talk you just heard previously, we know from our cosmological measurements that it would have to be very homogeneous, not changing too rapidly in time. So it would again have to be some very slowly rolling, very homogeneous scalar field, here roughly homogeneous across the entire universe. So it would look sort of something like this. And if you kind of compare these two and think about it from a detection standpoint, if I'm making a little detector here on Earth that's trying to tune in to this background field and observe it, they don't actually really look that different. If I'm just building, something like a radio here to tune into this background axion field, I'm just looking for a slowly varying, roughly homogeneous background axion field. So actually, you shouldn't be too surprised. The detectors that I can build looking for axion dark matter could also potentially have some sensitivity to dark energy, at least, as in the case that we'll discuss here, when the dark matter detector is looking for very low frequency, very low mass axions. Okay. So how could you look for it? Well, it should generically have several axion-like couplings to us. That's what we'd expect. That's what can allow the mass to be so low and can allow it to be slowly rolling. I'll just pick one to focus on, which is the coupling to nucleons. Here's the Hamiltonian term. This first G, that's the coupling constant. Think some very small number, some very weak coupling between the axion and us. By this sigma, I mean the spin of, for example, a proton, since I'll be talking about proton storage rings. And then this grad A is the spatial gradient of the axion field. And you can see from this Hamiltonian term that that's kind of acting like an effective magnetic field. Not acting like a magnetic field on individual monopole charges, but acting like a magnetic field on the spin of protons, for example. This gradient of the axion field is, in field theory, the spatial momentum of the axion. So if I'm sitting here, if I have some proton sitting here in the lab, and I have some background axion field with some gradient, you can see what it's going to cause. This gradient to the axion field is going to cause the proton spin to precess around whatever direction that axion gradient is in. And because it's in the direction of the spatial momentum of the axion, the direction in which the axion field is flowing, we call that the axion wind. So the proton spin would precess around the wind of the axion passing by the proton. And of course, as you saw in the previous slide, if it's dark matter, this is not a fixed spatial gradient. It actually oscillates in sign in time with frequency equal to the mass. So that's the signal you're looking for, this axion wind effect. And there actually have been many very nice high precision lab experiments looking for this signal based on technologies like atomic magnetometry, NMR, torsion balances, ultra cold neutrons. There's really been a lot of beautiful work done by many using many different experimental techniques to go after axions. And those all show a lot of promise. But I won't be talking about any of those. I want to talk about a rather different sort of test than a standard kind of high precision, high sensitivity, low energy lab experiment. So what am I talking about? Well, so here's our signal again. This gradient to the axion field is proportional to the velocity of the axion. But the problem is, as you know, that for dark matter, this velocity is 10 to the minus 3. That's the virial velocity in our galaxy, right? Or for dark energy, it looks even worse. The dark energy isn't really moving in the universe. Actually, that's in the cosmic rest frame. Of course, we're moving with respect to the cosmic rest frame. So in the lab, it would look like if the axion was dark energy, it would be moving at 10 to the minus 3. But still, either way, you can see whether you're looking for dark matter or dark energy, you pay this very large factor of 1,000 suppression to your signal. So that's sort of painful, but of course, with enough precision, you can try to get around it. We wanted to ask: is there a different way? Could I somehow remove this nasty factor of 1,000 suppression? Of course, it's generally pretty hard to take your atomic magnetometer or something and boost it to relativistic speeds. But of course, we can boost individual particles to relativistic speeds, and then hope to very precisely read out their spin precession. So, for example, here's a little cartoon of a proton with some big boost here. Even if the axion field in the lab frame, even if it was completely stationary, if it had no velocity at all, once you boost the proton and go to the proton's frame, the proton will see some very large gradient to the axion field. And crucially, it'll be in the direction of the boost. So you even control the direction of your signal, which is a very useful control parameter for the experiment. So what do we look for then? What's our signal? Well, if I take this boosted proton, and I jump to the proton's frame, you'll see from this Hamiltonian term, of course, that the spin of the proton should just precess in time, like the size of this coupling times time, right? This energy splitting H times time. So it's clear then I want really long integration times, which means if I want a relativistic particle, if I want to hold it for a long time, I should have a storage ring. I should go in a circle, right? But in that case, this axion effect we said was proportional to the velocity, was in the direction of the velocity, the boost of the proton. It keeps changing direction. So the effect would average down to 0, right? And so we actually wouldn't get any help of storing the particle for a long time. However, then we can make use of this beautiful idea from a while ago. People were able to design storage rings using the so-called frozen spin method, where you get the spin of, for example, the proton to precess at exactly the same rate as the proton itself goes around the ring, meaning the angle between the spin of the proton and its velocity always remains the same. No matter where you are around the ring, that angle remains the same. Then, of course, what happens is I don't average this effect down to 0. I can just keep integrating this effect for as long as I can hold the proton, essentially. This lets me avoid the velocity suppression, and so I can improve the signal just by having relativistic or semi-relativistic protons by this factor of 1,000. So the experiment then would be to inject protons in the ring, essentially let them go around using this frozen spin, and then this spin precession signal grows linearly in time, and you want to read out this spin precession rate. Now, the kind of really exciting part for me is that this experiment is really basically the same hardware, same idea as this beautiful idea to measure a proton EDM in a storage ring. And so, in fact, we could leverage all the really hard work that all those people have done, that collaboration has done, to figure out and simulate such an experiment. I won't go into the details of that proton storage ring EDM experiment, but it is really a beautiful experiment. And if you want to know more, I recommend bugging Yannis about that. Sort of to make a long story short, there's obviously many backgrounds for a high precision experiment like this. I won't go through them. They're in the paper, or happy to talk about them later. Basic idea is to have two counterpropagating beams going around this ring to cancel backgrounds. And then there's many specs. For example, you do need to measure and control the beam position to very high accuracy. But again, relying on our experimental collaborators, that appears to be achievable with many of the kind of advances that have already been worked on for this proton storage ring EDM experiment. So I'm going to kind of skip all that, which is really the hard part. but being a theorist, I can luckily leave it to my experimental collaborators and just kind of show you our results. Here is where we project the sensitivity. And I should say, this is really the same hardware, so it can be done with the same experiment. It's just yet more science that experiment can do, which is very nice. This is the coupling of the axion versus its mass. And here you see in gray the existing astrophysical and cosmological limits, for example, from emission from supernovae and things like that. And this blue line is where we project the storage ring experiment could go, kind of many orders of magnitude past current bounds, over these lowest masses, all the way down to kind of the fuzzy dark matter edge. And it turns out this would actually be one of the most sensitive searches for axion dark matter in this mass range. So I think this is a kind of a very exciting experiment. Let me kind of, since I'm out of time, let me skip the rest of this and just flash. Even for dark energy, you could have some reach into new unexplored parameter space. Here again is the coupling of the axion, this time versus the equation of state W of dark energy, or in other words, how much it is not a cosmological constant. And you can see this is the first experiment that I'm aware of that is able to push sensitivity to this coupling past the current bounds. Okay, so with that, let me kind of conclude and say I told you about these two ideas using trapped ions as detectors for millicharged particle dark matter, where we can already set new limits, and hopefully there should be significant improvements from in the future possible. And also using storage rings to look for axion dark matter and even dark energy in this lightest mass range. So thank you.
Thank you very much, Peter. You always give such exciting talks. Great. Any questions? I think people had most questions regarding the millicharged particles. Going back to that, as a matter of fact, I remember when we did, when we were looking for axion coupling to photons, you look, I mean, inevitably you put coupling to that as well. And in your plots, I was surprised I didn't see mu and G minus 2 or anything like that. It's to
the plots for the millicharged particle, you're saying?
Right, right.
Yeah, let me see if I hold on. This is not going to work very well. Sorry. Let me see if I can go back to that. I'm not showing all the possible bounds, but you can see we're working, pushed by cosmology and collider bounds and things like that. We're generally focused on these very heavy masses. I mean, you can see this is most of this parameter space is above TeV or so, and pretty small couplings. So that's challenging for that to make a significant boost. But I can find you the limits on that afterwards.
The mass is really high. I see. I didn't.
Yeah, well, there's these nice cosmology bounds down around 10 millieV or so, and astrophysics bounds, and also colliders, of course, can produce the particle. Even the edge of the collider bound, you can see, not surprisingly, is around a TeV. It's kind of a neat fact that we had to actually zoom out so much for this plot and expand the range, because these ion traps could actually look for a very wide range of masses.
Excellent, excellent, very good. Now we'll look into the microwave cavities, okay? Because these can do something then. All right.
I love it.
I'm waiting for a question so I can ask another one. In case of the storage ring, is it possible to do to look for clumped dark energy, you think is right?
Good. So it's a good question. So yeah, I think when you talk about dark energy, you always have to ask sort of what you mean in a sense. But I'd say actually let me see if I can just quickly share my screen again. If I go here, so when we're looking for dark energy, we are looking for it to have a non-trivial equation of state, meaning it's a dynamical field, meaning it can move, and if it can move, if it can roll in time, then it can clump. Let's say what the right thing to say. This would, of course, here we're still mostly focusing on the homogeneous component, but in principle, you could look for small gradients. Although I think you'd have to come up with a model in which you could source, what's the right thing to say? You need, I need a big enough gradient that it's going to be better to look for that than to look for the homogeneous component, which gets this boost from the relativistic speed. So it wouldn't be clear to me that I think generic models probably wouldn't have big enough gradients, but in principle, yes, I think.
Okay. Very good.
Oh, and I noticed I think there's a question in the chat, just going through the last question. Do you have sensitivity to axion-lepton couplings from the storage ring? Actually, that's a great question. So like an axion-electron coupling, and that's a great question for Giannis. So first, from theory, the answer is absolutely yes. We talked about the nucleon coupling only because of experimental, because you could make proton storage rings, for example, and people already thought carefully about it. But absolutely, this exact same signal would apply to the axion electron coupling. So Giannis, how can we do it?
Wow, something to think about, right? Yes.
I should answer one thing. For example, I don't think I have the backup slide, but you could ask about, for example, the muon G-2 experiment. We did actually evaluate in our paper the sensitivity of the current muon G-2 experiment to the axion muon coupling. And there, I would say, it loses a lot because it wasn't designed for this. It wasn't, the proton storage ring EDM experiment sort of beautifully, kind of accidentally, looks like it was made for this signal, whereas the muon G-2 not as much. So it doesn't actually get, the current muon G-2 doesn't get past the supernova limit on the axion muon coupling. But in principle, it's the sort of thing I think is very interesting, either with muons or there you suffer from the short lifetime, so probably electrons. But so Giannis will tell us how to make an electron story.
No, we can. It's the polarimeter that's the issue there. But the proton frozen spin method is the method looks solid. So that's very promising. Thank you for the question. Okay. Any other question? Well, Peter, as usual, you did it. Excellent presentation. Thank you very much for making time for it. Okay, thank you. Bye now. Okay. Well, this is the end of the session. Thank you.